Hi everyone. Um, I'd like to do a follow-up video on the specifics of Lorentz transformations because this is an issue that people often run into, and I realize that physicists, we tend to use units that are useful in a physics setting but can be kind of confusing to just about everybody else. And that's okay, but I want to make sure that you understand where we're going and you don't accidentally kind of double count the speed of light when we do these things. And I kind of got around this with the edits to the handout, but I want to do a little more explicit example. And what this deals with is the Lorentz transformations. And you can see some of this in the space-time simulator as well. So we can write the space-time transformations in the following way, right? So remember we have an unprimed frame and a primed frame. And in these, our primary variables are position and time. And sometimes we'll use W, which is this weird little unit so that things come out unitless. And remember that, generally speaking, we're talking, the prime frame is in motion with respect to the unprimed frame. Now, of course, they're both in motion with respect to each other, but this is the primary thing that we're usually talking about, and this is why we have these two diagrams that kind of overlaid on each other. Now, if we want to talk back and forth between frames, we need a way of translating what we see in one frame versus what we see in the other. In other words, if we want to measure or take what is seen in the prime frame in terms of what's seen in the unprimed frame, we know that t prime is equal to t minus vx over c squared, all divided by the square root of 1 minus v over c squared, right? And then similarly, we could do the same thing for x. X prime is equal to x minus vt over the square root of 1 minus v over c squared. Now, these are the Lorentz transformations. And they're different from the Galilean transformations because in both time and space, you can see that time and space occur for the time equation, and time and space occur for the position equation as well. These are also designed so that when you look at differences, delta x over delta t, for example, you get no speed that's greater than the speed of light. Now, the trick here, I'll move this up a little bit, is when we start using these weird units. Now, these are fine. If you have all of these in SI units, then you're fine. If x is measured in meters per second, c is in meters, and c is meters per second, and time is seconds, you're all good to go. And as long as you use c as 3 times 10 to the 8 meters per second, you're fine. But often, when we talk about these things, we want to use what are called normalized space-time units. And the reason for that is that it makes our life easier with these space-time diagrams. Now, we get to that by making a couple of substitutions, or at least make the name of these variables. So we're going to call the Greek letter beta, we're going to define that as v over c. So these three equal signs means we're defining beta as basically the speed is a fraction of the speed of light. And you can see that this would be in meters per second squared, and this would be in meters per second squared. Okay. If we do that, then we can also define gamma as 1 over the square root of 1 minus beta squared. Both gamma and beta are now unitless. Right? Beta is always going to be less than 1. gamma is always going to be greater than 1 because 1 minus something small is always going to be big. And of course, nothing can be greater than the speed of light. So what does this do for our Lorentz transformations? So now we can write the Lorentz transformations in their normalized space-time units. Okay, so now t prime, let's get green here. If we follow this through, we get ct prime, which we'll call w prime. See, that's why we have these w's here, is equal to gamma, because we have 1 over the square root of 1 minus v over c squared times w in the unprimed frame minus beta x, where here x is going to be in those normalized units, usually light seconds or light years. Then we can ask what is the equivalent for x prime, and in these units x prime is going to be equal to gamma times x minus beta w. Now I'll let you confirm if you substitute those in, that's what you get. But this is now probably the easiest way that you can write the Lorentz transformations, especially if you have v over c. And this means that you don't, when you write it this way, you do not need, in fact you shouldn't, write out c explicitly. And I'll show you what I mean by an example. But take a second to look over the green box and compare it to these equations up here. They're exactly the same. We've just replaced beta, v over c for beta, and we've replaced 1 over v minus 1 over vc squared square root with gamma, and we had to pop out an extra c, and that's where our w prime came in and our w came in. Okay? Take as long as you need to make sure that you understand that. Pause this if you need to. Okay, so let's look at an example. We'll do this algebraically first. So, for example, let's suppose that the primed frame is moving at a speed of 4/5 the speed of light. That is, v over c is equal to beta is equal to 4/5, or 80% the speed of light. Okay, and now let's further suppose that we have two events in the unprimed frame. Let's call it event 1, has coordinates x equals 1 and time equals 0, and event 2 has a coordinate of x equals 3 and time equal 1. We want to know then what are the space-time coordinates in the moving frame that is moving with respect to this unprimed frame with a speed of v over c is equal to 4/5. In other words, we want to know x prime and t prime for both those events. Well, we need to use the Lorentz transformations for each case. Okay? So, let's do the first event, so number 1. We can compute x prime is equal to, now, first we need to find gamma, right? So we know it's going to be gamma times w minus beta x. But what is gamma? Gamma is equal to 1 over the square root of 1 minus beta squared. So that's 1 over the square root of 1 minus 4/5 squared. That's 1 over the square root of 1 minus 16/25. That's equal to 1 over the square root of 9/25. And that's equal to 1 over the square root, excuse me, ahead of myself, 1 over 3/5 or 5/3. Oop. All right, 5/3, right? So gamma equals 5/3 when beta is equal to 4/5. Like I said, beta is always less than 1, gamma is always greater than 1. Okay, so let's find this value. Remember, x is equal to 1 and time is equal to 0. So x prime now is equal to gamma, that's 5/3, times 1 minus 4/5, that's beta, times 0 now, that's the time, or 5/3. Okay, now t. T prime is equal to 5/3. And in this case, we can call this W, right? I mean, we are technically solving for W prime in this case. So this is really CT or W prime. And as long as we're using seconds and light seconds, years and light years, it won't matter. But now to solve this in these unitless, in this normalized units, we still have gamma is equal to 5/3. We go back to our equation. This is now 0 minus 4/5 times 1. That is, we put in our value of t here and our value of x here, whereas we put in our value of x here and our value of t here, right? I'll put x here, t here, x there, right? And that's equal to minus 4/3. Okay, so for event 1 in the primed frame, we have space-time coordinates of 5/3 and minus 4/3. Remember, it was 1 and 0. Okay? So that's the first event. Now the second event is x equals what would we say? X equals 3 and 1. So x equals 3, t equals 1. Right, so now x prime is equal to 5/3, and now we put in t, that's 3, minus 4/5. We put in x, that's 1, and that's 11/3. Okay? ct prime, w prime, is equal to 5/3 times 1 now, minus 4/5, 3. Or, once you work all of that out, minus 7/3. Did that math right? So event 2 in the prime frame has space-time coordinates of 11/3 and minus 7/3. Okay. All right. So what does this mean? That means that we have one frame in which the order of event, or the events are, excuse me, x and we can call it w, since we're in normal units, are make sure I have this right, are 1 and 0, right? X prime and w prime are 5/3 and minus 4/3. So both x and t change, This is event 1. Event 2, x and w is 3 and 1. X prime and w prime are now 11/3 and minus 7/3. Okay, so these are two events, and I want to take a second here to explain exactly what it is we're doing. We're observing. You imagine that you're on a plane, say you're on a frame, and you see two events, right? And then somebody else outside that frame is moving past you and sees those two events. And you both, if you're here on this frame and you see these two events, you have one explanation. This person who's moving by sees something else. I discussed this in the lecture with the Galilean transformation about the difference between someone being in a train and dropping a ball up and down, and it just looks like it's going back and forth. But outside the train, because the train is moving, the ball looks like it's making this curved path. The Galilean transformation is a way of talking between these two frames and seeing that they are basically two sides of the same coin. The Lorentz transformation does something similar, but has a much deeper meaning because of the connection between space and time. So what does this all mean in terms of space-time diagrams? Well, I'm glad you asked that. Let's draw a space-time diagram of this event, for these events. So here's our unprimed frame, x and w, right? And we know that we have one event at x equals 1 and w equals 0. Okay, so this is in light seconds, and we'll call this in seconds, right? Technically, c times seconds, right? Because w is equal to c times t. The reason why we're doing this is so we don't ever have to multiply c to these transformations. If we don't use these normalized units, then you have to include c. Okay, so this is event 1 at x equals, it's going to get messy here. This is event 1 at x equals 1, w equals 0. Then event 2 is at x equals 2 or 3, so 2, 3, and then time w equals 1, so right there. This is event 2. And so we can see that event 1 happens, then event 2, and you should ask yourself, can event 1 cause event 2? I'll leave that for you to think about, and if you want to talk to me during office hours, we can certainly look at that. But there's a very simple trick for being able to tell whether this is, in fact, what we call space-like or time-like intervals. Now, this is for the unprimed frame, right? What we often call the lab frame. Now we have a frame that is moving, so the primed frame is moving with the speed beta equals v over c equals 4/5. Now what? Well, we know that the x and the w axes bend towards the diagonal, and that angle is equal to, or tangent of that angle alpha is equal to beta, that is v over c. And so it's rather easy, given that this is 4/5, we can just count 1, 2, 3, 4, 5, 1, 2, 3, 4. Let me erase these things here. Well, I'll keep that here. Right, this is 1, 2, 3, 4, 5. 1, 2, 3, 4. This is now our x prime. And in the similar way, 1, 2, 3, 4, 5. 1, 2, 3, 4. This is our t prime, or I'll just call it w prime axes. They're bent pretty significantly, right? And that's because this is moving pretty close to the speed of light. This angle alpha is equal to the arctangent of 4/5. And if we wanted to, we could even draw in the line that bisects them, right? And that's the line that indicates the speed of light. Now, what does this all mean? If you are in the primed frame, you have a different measurement system. Both the x divisions on this line and the w prime position on this line have different distances than in the unprimed frame. They don't have the same spacing. And one way you can tell that is to try and find where these x prime and w primes occur for these events. One way we can do this, we can extend these lines backwards, right? So this is basically negative w prime, and this is negative x prime, right? If we just follow those arrows. Now, to read off anything from a graph, if you want to read, say, this position for event 1, and you want to read its x coordinate, x prime coordinate, and w prime coordinate, you follow the axes that is perpendicular to the other axis. So, for example, if you want to know what the x prime coordinate is, well, let's look at the w prime. You look at where this is going to intersect. You draw this back. See how this line here is parallel to the x prime axis, and you draw it back until it reaches the w prime axis. Okay? And you can do the same thing up over here for event 2. Right? It's a little trickier, but you can do the same thing and draw this back until you get to w prime. The same is true for getting to x prime for event 1. Here, you're drawing towards, right, the w prime axis, right? The x prime axis. Overshot there. Oh, no. There we go. You draw this line until you get to the x prime axis, right? And you can then read off, if I drew this carefully, the space-time coordinate now for in x prime and w prime, you should be able to read off from this x prime axis intercept and this w prime intercept, and it would be 5/3 and minus 4/3. Okay? You should be able to do the same thing for event 2 now. So event 2, if we draw this back, we get its time, right? And if we draw this forward, again, parallel to those other axes, we get its space. And then if we look at event 2, see x prime, w prime is equal to 11/3 and minus 7/3. Okay, so what does this tell us? Well, there are a couple of things. The Lorentz transformation gives you a way of going from x and w to x prime and w prime. And there's an inverse transformation too, so that if you need to, you could also, if you knew what x prime was, go the other way, x prime, w prime to x, w. We don't always do that, but you could do that. Not only that, but this diagram allows you to see that when you're in the moving frame, the order of events has changed. Because event 2 happens at an earlier time, that is farther in the past, the order of events in prime frame is 2, then 1. In the unprimed frame, it's clearly 1, then 2. Now, you could, and I'll set this up for you to work on your own, what if beta were equal to minus 4/5? If that's the case, these axes bend the other way, and the order gets changed yet again. Okay, that was the basis of the first concept test we had today. The way in which we travel matters for the order of events. Okay, I want you to pause this if you need to and look over this. Get out a piece of graph paper and see if you can replicate both the algebra and the graphics for something like this. This will be very helpful for that last problem on the problem set. Okay, one last thing.